Hey there, welcome back to Short Takes 331. Today we're going to see another example of a Fourier series. We're going to expand the sine of x to the nth power. And for that purpose, we're going to go ahead and use the exponential form of the Fourier series. If you recall, that's for a given function f of x between with an interval for x between minus pi and pi. The Fourier series in exponential form is given by this formula. So the sum from k equals minus infinity to infinity of some coefficient, which is our Fourier coefficient c sub k, e to the ikx. And normally these coefficients are calculated by this formula. Ck is 1 over 2 pi, the integral between minus pi and pi, f of x e to the minus ikx dx. But in this case, we're going to do this without integrals. So we're going to use something called the binomial theorem. And if you haven't seen that, don't worry, we're going to see a derivation of that in a future video. For now, we're just going to use the result. And to apply that result, we're going to write the sine of x to the nth power as e to the ix minus e to the minus ix divided by 2i, the whole thing to the nth power. In other words, the sine of x is this combination inside here, which is something we saw in a previous video, and you should go check it out. The video on Euler's formula contains these expressions. And the binomial theorem tells us that when you have the sum of two terms elevated to the nth power, you can write that as this sum in this way. So a plus b to the nth power is the sum from q equals 0 to n of the combinatorial coefficient nq, which is given by this formula here, times a to the q, b to the n minus q. And of course, you can choose what you call a and what you call b. We can in fact flip a and b and put b here instead of a and a here instead of b. So there's a symmetry in this formula between the terms at the close to n and the terms close to 0. We'll get back to that in the video on the binomial theorem. But for now, we're just going to use this result as written here, and remember then that this binomial coefficient is simply given by n factorial divided by q factorial times m minus q factorial. So this is just a formula. Now we have a 2i to the nth power here in the denominator, so we're just going to pull that out of the sum right away. This is 1 over 2i to the nth power. And now we have this sum, and we have to choose what we call a and b, and of course we're going to have to choose what's a and what's b here. We're going to take this guy to be a with a minus sign. That's going to be our a, and b is going to be our e to the ix. And so if we do that, then we get the sum down here from q equals 0 to n, our combinatorial coefficient nq, minus 1 to the q, this comes from this coefficient here. That's going to be our a, like I said, e to the minus iqx, again, that's just this part, elevated to the qth power. And then this is going to be our b term, and so that's e to the I n minus q x, and that corresponding to the a and b in this formula. And so now simplifying further, we see that 1 over I to the nth power is actually minus I in the numerator to the nth power. And so we have 1 over 2 to the n, and then minus 1 to the n, I to the n. So that's just putting this I in the numerator. We didn't have to do that. We could have left it in the denominator, and that's totally fine. And then we go on, we have the sum from q equals 0 to n, our combinatorial coefficient, minus 1 to the q. And now we can unify these two exponentials very simply by saying this is e to the I n minus q minus another q. So it's e to the I n minus 2q times x. And so this is where we're getting very close to making something look like what we want, like our Fourier series, except that we really want to find the coefficients of e to the I kx, and we want to have then a clean sum from k equals minus infinity to infinity, and see that it really takes this form. And so, in other words, what we see in the exponent here that's called n minus 2q, that's our k. And so suppose we call that k, and so then what happens? Well, then for q equals 0, k must be equal to n, because if q is 0, this is just n. For q equals 1, k is n minus 2. For q equals 2, k is n minus 4, and so on and so forth. And so when q equals n, the maximum value you can take, then we have that k is n minus 2n. That's to say, k is minus n. And so what we have here, clearly it's a sum that goes from n to minus 2n, if you want from minus n to n, and that skips every other value. So we only need, we don't see here n minus 2, we don't see n minus 1, we don't see n minus 3, we don't see n minus 5. So all those n minus some odd number, all those are skipped. And so in a way, then what we have is a sum from minus n to n for k of coefficient c sub k and e to the I kx, where c sub n is given by this coefficient corresponding to, again, k equals n would be q equals 0. So if you go and read the value of the coefficient for q equals 0 here, and you attach also this part, then what you get is 1 over 2 to the n minus 1 to the n I to the n. That's just coming from here. And then the q equals 0 term will give you n0, that's just 1, minus 1 to the 0, that's just 1, and nothing else. And so that's what we have here. We can simplify this further. I'm just going to leave it like this. Then we have cn minus 1, which is nothing. There's no n minus 1 coefficient, because remember we go from n to n minus 2, and so there's no n minus 1, and so that's just 0. There's cn minus 2, that corresponds to q equals 1, and so we go up here and we read what happens for q equals 1, and so we have this prefactor as always, then we have n1, which is easy to find, and then minus 1 to the 1, which is just minus 1, and so that's what I wrote down here. That's what I wrote down here. So there's minus 1 coming from minus 1 to the qth power with q equals 1 is what gives us a plus 1 up here. And then we have the combinatorial coefficient n1. Cn minus 3 is 0, and so on and so forth. So you continue down this pattern until you get to the last value, which corresponds to k equals minus n. Remember that we saw up here that when q equals n, the maximum term here, the maximum value of q, then we have the k is minus n. And so in that case, c sub k for k equals minus n is just 1 over 2 to the n, I to the n, and then the combinatorial coefficient nn, which is also just 1. Now, that's it. That's basically all there is for this Fourier series of sine of x to the nth power. All we have then is that we have a sum that is finite. It goes from k equals minus n to n. There's some coefficients c sub k that are given in this table. You could complete the table more carefully if you want, but there's nothing more than that. The highest frequency modes are plus and minus n. Those are the highest frequencies present in the series to the nth power of the sine of x. You could expect the same thing for the nth power of the cosine of n, and I'll let you prove that. The proof is following exactly the same steps. This series is actually a finite sum then. It terminates, so it does not go from minus infinity to infinity. There's all those terms are mostly 0 except the ones that go between minus n and n. And half of those between minus n and n actually vanish, because we have that cn minus 1 actually vanishes, cn minus 3 vanishes, and so on. So between minus n and n, it looks like you might have two n plus 1 coefficients, but actually half of those vanish, so you don't have to worry about those. Furthermore, you can check that the full result has to be real, and so it must be that the coefficient c minus k is actually ck star. And you can check that here, where I wrote cn and c minus n. You can see that c minus n is actually this one, the complex conjugate. If we complex conjugate this term, then we get minus I to the n instead of I to the n, and so that becomes this one, and vice versa. If you complex conjugate this guy, you get minus I to the n, and that's just this minus 1 to the n that appears here. So you always have this property that the Fourier series coefficients order minus k are equal to ck star if you expect the full result, if you accept the sum to be real. And that's what we expect in our result, because the sine of x to the nth power is just real because the sine of x is real. So let's prove that this property has to hold. This is very simple to see. So suppose you have this expansion, this Fourier series from in exponential form, and you take the complex conjugate of the whole thing on both sides. So okay, so then we have f star on the left, and on the right we have c star, and e to the minus ikx, because that's how you complex conjugate the exponent. Now we can change notation and switch from k to minus k, and we have a sum still from minus infinity to infinity, but now instead of where we see k here, we put minus k, and so this minus sign then disappears in the exponent. So now we can compare what we see for f of x and f of x star, and of course we know that if f of x is real, then f of x has to be equal to f of x star. But then if that's true, then the coefficient ck must match the c minus k star. Then because these sums must be equal, and so each mode has to be accompanied by the same coefficient because they're all linearly independent. And so it must be then that c minus k is ck star. If you see here, it's a little bit written slightly differently. It says c minus k star equals to ck, but it's exactly the same as writing it in this way. And so we have proven then that indeed if the full result is real, we must check that c minus k is equal to ck star, which is another result of this video besides our main result, which is the Fourier series expansion for the sine of x to the nth power, which is given by this sum here and these coefficients. And that's it. That's all I have for you today. I hope you enjoyed this video. If you did, please like and subscribe. As always, if you're looking for a tutor in physics or math in English or in Spanish, you can contact me at showtext331 tutor@gmail.com, or you can leave a message in the comment section below and I will get back to you. And that's all. Until next time.